Hello, hi everyone. So let's recap last week's synthesis in VLSI part 1 and then we'll go to part 2 of synthesis in VLSI today. So we from Semicon Technolabs, so we are established VLSI and embedded uh, training center with over 8+ years of experience headquartered in Bangalore and branch in Hyderabad. Now, last week we discussed about ASIC design flow, where we discussed about system specification, where an idea is taken as what kind of chip we want to make, followed by mapping the idea into architectural design. Right? I mean, where we map the idea into architectural document. Again, it is consisting of analog and digital. Now, since synthesis is predominantly defined by digital portion, so we talk about digital side. So digital architectural design is mapped into RTL design by the designers, and from there we do the functional simulations in order to make sure that RTL is working as expected. And after that, this golden RTL is mapped into synthesis. So this is where we are trying to get the uh, net list. Okay, so synthesized design, right? And post that it is physical design followed by mask preparation, fabrication, packaging and testing, right? And finally chip, right? Now let's go to what is synthesis. Let's recap part 1. What is synthesis, right? So synthesis is the process of converting a high level hardware description language design into gate level netlist. The goal of synthesis is to generate a gate level netlist that meets the design specifications and constraints such as area, power and timing. Now inputs to synthesis: RTL code, logical library, physical library, technology file, wire load model, synopsis, design constraints, unified power format, right? RTL code, right? What does RTL code contain, right? So RTL code contains 4-bit adder in Verilog, right? Now if you see here, this 4-bit adder in Verilog, which is nothing but adder 4-bit, this has been mapped into gate level netlist, right? The same module name is coming here, and then the functionality that is defined in the RTL has been mapped into technology dependent gate level netlist using the XOR and AND gates, right? Now, sample module in RTL, right? I mean, this is how the sample module is, AND module, right? And then we have outputs and inputs, and then the functionality is defined here, right? Now, let's look at the .lib logical library file. So, Liberty file, which is nothing but .lib or .db file, it contains cell logical view, standard cell lib, gate delay function. Lib contains cell type and functionality, delay models, which can be wire load model, NLDM, CCS, right? Pin and cell timing and design rules, PVT conditions, power details, right? The combinational cell info that is present in the library is cell name, area, and then DRVs, right? And then we also have capacitance, right, which will dictate the dynamic power. Okay. Now let's look at the sequential cell info in .lib file. Okay, so sequential cell D flip-flop POS, right? I mean, we have the leakage power, and then we have footprint, area of the cell, and then timing information. Okay, and then we also have internal power information as well. Now let's recap on the lookup tables which we learned last week, right? This is how the lookup tables will look like. This is used for calculating the cell delays. So mainly based on the input transition and output load. Okay, .left file, physical library. So this contains cell name, shape, size, orientation and class, port or pin name, direction and layout geometries, antenna diff area, obstruction, blockages. So macro. So the macro contains class block, right? Origin, right? And then size, symmetry. So this is how the macro definitions are, right? I mean, use signal, direction, input, right? And the metal layers, because this is physical library. Okay, standard cell info into left. So even in the standard cell left file, right, just like the macro left file which we studied in the previous slide, we will have class core, origin, size, site unit, and then pin, direction, and then metal layer related information, right? So this is mainly for the physical aware synthesis. Okay. Then tech file. The tech file contains units and design rules for layers and vias as per the technology, name and number conventions of layers and vias, physical and electrical parameters of layers and vias, manufacturing grid definition. Okay, this is how the tech file contains. Okay, you can see here the layer name, right, and then layer number, mask name, pitch, right, and then the color of the metal layer, minimum width, max width, minimum spacing, default width, same net, min spacing, right. All these attributes are present in the tech file, which we use it for physical aware synthesis. Now, tech file into infos, right? Design rules, layer name, right? Similarly, design rules for the layer name and min enclosure, end of line, right? And similarly, density rules, right? What is the minimum density? What is the maximum density? Window size, right? All these things are again defined in the tech file. Now, UPF is used when we want to optimize the power, right? So UPF is coming from the RTL team and it is given to synthesis team. Synthesis team output UPF is given to PNR team. So unified power format is a crucial file used in design for power intent specifications during the implementation of complex integrated circuits. UPF plays a vital role in low power design techniques, enabling designers to manage power domains, power modes, and power related constraints efficiency. Right, UPF file contains power domains. Some time design have more than one power domain like multi-VDD design, and sometimes only a single power domain. In this group of elements share a common set of power supply. So supply rails, additional protection by special cells which are nothing but level shifters, isolation cells, power switches, retention registers. UPF file snaps, right? I mean, these are all the different contents that are present in the UPF. It can be ground net, it can be power net, right? And it can be supply set, power domain, right? And then even the power switch related information, isolation cell related information, power state table is present, right? These are all the main contents of UPF, right? And apart from that, even the port attributes are present in the UPF with respect to power and ground. Now, TLU plus files, this is again used in the physical aware synthesis. So, TLU plus files is a binary table format that stores the RC coefficients. The TLU plus models enable accurate RC extraction results by including the effect of width, space, density, and temperature on the resistance coefficients. The map file matches the layer and via names in the Milky Way technology file with the names in the ITF, right? The main function of this file can be given as finding RC parasitics of metal per unit length. These parasitics are used for calculating net delays. Right, wire load models. These are again present in the .lib file. The wire load group contains information that DC utilizes to estimate interconnect wiring delays during the pre-layout phase of the design. These models define the capacitance, resistance, and area factors. In addition, the wire load group also specifies slope and fan-out length for the logic under consideration. The capacitance, resistance, and area factors represent the wire resistance, capacitance, and area respectively per unit length of interconnect wire. Right? Now, SDC file. Right? I mean, SDC file mainly contains clock definition, timing exceptions. It can be false paths, multi-cycle paths, right? Min and max delay. Right? Now, the SDC file, a sample of SDC file is present here. So create clock, set clock groups, set input delay, output delay for the interface timing, and set load for the all outputs, case analysis in order to switch between the functional clock and scan clock, right? Now, this is about the recap of part 1 of synthesis, which we discussed last week. Now let's go to part 2, okay? So part 2, let's go a little deeper into synthesis. Okay, synthesis transformation. Synthesis is nothing but translation plus logic optimization plus gate mapping. Okay, from RTL source it is translated into generic Boolean gates. Okay, and now from generic Boolean gates along with the timing constraints it is optimized plus mapped by using the compile ultra command, which is nothing but technology specific gates. The verb to compile is used synonymously with to synthesize. Right, synthesis environment. As with most EDA products, Synopsys tools require a setup file that specifies the technology library, location, and other parameters used for synthesis. Synopsys also defines its own format for storing and processing the information. Startup files. There is a startup file called .synopsys DC setup. This is applicable only for the Synopsys based DC compiler. Right. It is in tickle format and contain path information to the technology libraries and other environment variables. The default startup file for DC resides in the Synopsys installation directory and is automatically loaded upon invocation of the EDA tool. It can be DC, DC compiler, DC graphical, DC topo, right? This default file do not contain the design dependent data because this is mainly for invoking the tool, right? This is internal Synopsys files. Its function is to load the Synopsys technology independent libraries and other parameters. The user in the startup file specifies the design dependent data. During startup, these tools read the files in the following order: Synopsys installation directory, user's home directory, project working directory. The settings specified in the startup files residing in the project working directory override the ones specified in the home directory and so forth. That is, the configuration specified in the project working directory takes precedence over all the other settings, right? It is up to the discretion of the user to keep these files wherever it is convenient. However, it is recommended that the design-dependent startup files be kept in the working directory. Always it is recommended that all the files which you need for invoking the synthesis tool, it is present in the working directory so that it becomes easy for the tool to get the needed files and to load the files as well, right, into the tool. Now, synthesis library, system library variables. The target library, link library. These are the two common terminologies which we keep using in the synthesis. The target library specifies the name of the technology library that corresponds to the library whose cells the designers want DC to infer and finally map to. The link library defines the names of the library that refers to the library of cells used solely for reference. That is, cells in the link library are not inferred by DC. For example, you may specify a standard cell technology library as the target library while specifying the technology library name and all other macros, RAMs, ROMs, etc. in the link library list. This means that the user would synthesize the design that targets the cells present in the standard cell library while linking to the pads and macros that are instantiated in the design. If the pad library is included in the target library list, then DC may use the pads to synthesize the core logic. The target library name should also be included in the link library list. This is important while reading the gate level netlist in DC. DC will not be able to link to the mapped cells in the netlist if the target library name is not included in the link library. Right? You have to be very careful on how to use the link library and target library. For this case, DC generates a warning stating that it was unable to resolve reference for the cells present in the netlist. The target library and link library system variables allow the designers to better control the mapping of cells. Right? These variables also provide a useful means to remap a gate level netlist from one technology to another technology. It can be from 3 nanometer to 2 nanometer, 5 nanometer to 3 nanometer. Right? In this case, the link library may contain the old technology library name, while the target library may contain the new technology library name. Right? Symbol library. The symbol library system variable holds the name of the library containing graphical representation of the cells in the technology library. Right? So it is used to represent the gates schematically while using the graphical front-end tool. Right? The symbol libraries are identified with a SDB extension. If this variable is omitted from the setup file, tool will use a generic symbol library called generic.sdb to create schematics. Generally, all technology libraries provided by the library vendor include a corresponding symbol library, right? Design entry. Let's talk about design entry. Before synthesis, the design must be entered in DC in the RTL format. Okay, it should be structured RTL, not the behavioral RTL. Okay, so from the behavioral RTL only structured RTL will come. The structured RTL, after passing the functional simulations, has to be given to the DC for synthesizing and providing the netlist. DC provides the following two methods of design entry: read, analyze, and elaborate. Okay. The analyze and elaborate commands are two different commands allowing designers to initially analyze the design for syntax errors and RTL translation before building the generic logic for the design. The generic logic is nothing but GTech components or part of Synopsys generic technology independent library. They are unmapped representations of the Boolean functions and serve as placeholders for the technology dependent library. Right? Now the analyze command also stores the result of the translation in the specified design library. It can be Unix directory that may be used later. Conversely, the read command performs the function of both analyze and elaborate commands but does not store the analyzed results. making the process comparatively slow, right? Analyze, reads an HDL source file, check it for errors, creates HDL library objects in an HDL independent intermediate format, stores the intermediate files in a location you define if the analyze command reports errors. Fix them in the HDL source file and run analyze again. After a design is analyzed, you must reanalyze it only when you change it. Right? So this is the first step. It is mainly focused on reading the HDL source and checking for any errors. Right? Now next step in the synthesis is elaborate. First step is analyze, second step is elaborate. So translates the design into technology independent design, that is GTech, from the intermediate files produced during analysis. Allows changing of parameter values defined in the source code. Replaces the HDL arithmetic operators in the code with a design-ware components. Automatically executes the link command which resolves design references, right? Now in the synthesis, as we read earlier, first step is from RTL source to translate into generic boolean gates, from there to technology specific gates. Okay, now sanity checks, right? What are the main sanity checks which we have to focus on? Library checks, design or netlist checks, SDC checks, right? Now check library. This command shows the name of the library, name of the file, library type and version, time unit, capacitance unit, leakage power unit, current unit, and it shows the number of cells missing, number of metals or pins missing in physical and logical library. It performs consistency checks between logical and physical libraries. Suppose if designer forgot to load either HVT, LVT or .lib, then there will be inconsistency. It checks library qualities in three main areas: physical library quality, logical versus physical library consistency, logic versus logic library consistency. Right? Check design. It checks the quality of netlist and identifies floating pins, multi-driven nets, black box module, undriven input ports, unloaded output ports, unconstrained pins, pin direction mismatches. All these things are checked in the mega command check design, right? Now check timing is another mega command. Only when check design is clean and understandable, then only please go for check timing, because first design checks are important, followed by timing checks. So clock reaching all the clock pins or flops or not, ports missing input or output delay, right? Ports missing slew or load constraints, multiple clocks driving same register, unconstrained endpoints, combinational loops. All these things are checked in the check timing command. Then optimization process. Design compiler performs the following three levels of optimization: architectural optimization, logic level optimization, gate level optimization. Okay. Then architectural optimization. Except for design-ware implementations, these high-level synthesis tasks occur only during the optimization of an unmapped design. Design-ware selection can recur after gate-level mapping. Right? High-level synthesis tasks are based on your constraints and your HDL coding style. After high-level optimization, circuit function is represented by GTech library parts, that is by a generic technology independent netlist. Please remember, GTech is a technology independent netlist, whereas a final netlist is a technology dependent netlist. Right? Logic level. Flattening. The goal of this process is to convert combinational logic paths of the design to a two-level sum of products representation. It is useful for speed optimization because it leads to just two levels of combinational logic. Structuring. The resulting structure is then mapped to gates using mapping optimization techniques. Right? I mean, as you can see, unoptimized design, then logic optimization, gate optimization, optimized design. Gate level optimization. Gate level optimization works on the generic netlist created by logic synthesis to produce a technology specific netlist. It includes the following processes: mapping, delay optimization, design rule fixing, area optimization. Right? Now reports. What are the different reports that we get from the synthesis? Timing report, QR report, report area, report power. So these are the different reports that we get from synthesis. Okay. So and then apart from that, what other inputs? Netlist, right? See, technology dependent gate level netlist, right, which will be used for either DFT insertion or which will be used for PMR if the DFT is not done, right? Again, the netlist will be containing the scan insertion as well, which is part of DFT. Okay. Then SDC file, which is output of synthesis. The SDC file will be containing create clock, create generated clock, set load, set driving cell, set input delay, set output delay, set clock uncertainty, set max transition. All the commands related to clock, all the commands related to generated clock, all the commands related to design margins, which are uncertainty, right? all the commands related to interface timing, which is set input delay, set output delay, right? So all these things are present in the SDC file. Then scanf. Scanf is the output of scan chain insertion. It contains number of scan chains, right? And how many elements are present in each scan chain, right? All this information is present in the scanf. Okay. So with this, we come to end of today's part 2 session. Let's all catch up next week again for part 3 of synthesis in VLSI. Okay. So with this, have a nice weekend, and we'll all catch up again next week in the same YouTube live presentation from Semicon Techno Labs. Thank you. Thank you so much.